be talking about vulnerability and implementations of SHA-3, Shake, DSA, and other NIST-approved algorithms. And this is joint work together with Christopher Seeley. So first, because I like to start with an easy slide that hopefully everybody can still follow, and then it gets progressively more difficult from there on. So here is an example of what a hash function looks like. Most hash functions are iterated hash functions. What will happen is that there's this type of function that you will keep calling again and again. After you've split the message, possibly after padding into blocks of fixed size, so that you can process a variable length message using some fixed length underlying calls. At the end, you'll have hash value that is computed, and I put like a little fingerprint next to it because the idea is that hash value uniquely identifies the file. So it shouldn't be possible to construct two different files with the same hash, or also not like you're given a hash value to work back and try to find out which message matches this or which file matches this specific hash. There are two interfaces for hash functions that are common. First one is hash, where you would provide the entire message, the entire input at once. So it's like a one-shot interface. And then another is one where you can provide the message in different sized chunks. And these chunks do not necessarily have to be the same as the fixed block size that I was showing in the previous slide. So I also try to indicate this here, like some update might have a small call or might have like a very big amount that you're passing in. And then you have final that you need to call at the end to say, I'm done hashing now, please finalize whatever you want to do and output the resulting hash value. So RSA likes interactive sessions and interactive talks. So I have a first question here. Does anybody know where or when these two interfaces are being used? Yeah, no, like I gave this talk already in Austin and in Tokyo, so I could call out the people over there. Yeah, go ahead. Go to Mike maybe, or like, yeah.
I guess the first one for files and the second one is for streams.
So it, like, I think that's not a bad answer, right? Because if you're reading from a file, then when you access parts of that file, if you map that file into memory, you might get a bus error when you do a memory read, right? So it can be a much cleaner implementation if you say, I'm going to read a certain amount of bytes in, put that into my memory, and like check if there's a read error before that, and then like you verified already whether something might have gone wrong when you're reading in the message. So I would say that's correct. Like there are, it's more common if you hash a file that you would use this init update final, where the update is taking parts of the file in. The file might be quite large. The main thing I wanted to say here, because like usually I would get the wrong answer and have to say why the answer is wrong, but this audience here only gives the right answers. Okay. Usually people would say, well, clearly update is what I need to do if I have a large amount of input, because then I can do it in smaller blocks. But that's not necessarily the case, because whether your input is large or small, you can just pass it on to the function. Like it shouldn't matter what the size is, just like let the underlying logic deal with splitting it into blocks. Typically, update is used in places where you want to avoid a temporary buffer. And places where you would have a temporary buffer is when you need to, for example, hash different parts that you want to put together, and then you don't want to, you don't want to do a copy of everything into a temporary buffer. You just want to pass on what you have to avoid that copy. And similarly, if you're going to hash something like A, AB, ABC, or like there's a hash of a message that keeps scrolling, and in between you need to compute the hash values, you'd also need to, if you don't have this init update final, you need to make an unnecessary copy to store all of the message so far. And the same came up with this file example, actually, because if you want to ensure that when you read, you check if there was a read error from a file, then you also want to avoid the temporary buffer there. Don't store your whole file into this temporary buffer, but as soon as you read a part and check that it's been correctly read, pass it on to the buffer. So now that we talk about a few bugs, so here is a bug that was present since 2008 when the SHA-3 competition started. And a few years after the competition finished in 2015, the bug was disclosed. It's related to one of the 5 finalists, in this case Blake 256. So there's also a Blake 512, but for Blake 512, the message is processed of blocks of 128 bytes. So just to make it easy, I'm only looking at this smaller size of the hash function, where the message is processed in blocks of 64 bytes. And then if we consider that you are doing, of course, first init to initialize the data structure, then update on an input less than 1 block, then update on an input of exactly 1 block, and then you finalize. And what happens is this first call is actually sort of forgotten due to a bug in the implementation. So what that means is that actually you've constructed a second pre-image, but not for the algorithm of the hash function, right? So like an important thing that sometimes confuses people throughout the presentation is there's actually nothing wrong with the standards document or with the specification of the function, but the problems here are impacting the way that a particular implementation has done has implemented the algorithm incorrectly. So then not for the hash function, but for the specific implementation of this hash function that was submitted to the competition, you can construct second pre-images, meaning that if you already have a message with or without this update, the hash will be the same. So you can, given a message and a hash value, construct another message that has the same hash value for this implementation. Here, 3 years ago, on the same stage, like I see nothing has changed about the layout for CTRSA and for RSA, I gave a talk about a bug that I found in Apple Core Crypto. This was before the pandemic, for those who still remember pre-pandemic times. So Apple Core Crypto is the cryptographic library that Apple uses inside of all of their devices. And there was a bug that affected all of their hash function implementations because they all shared the same code except for one. And this was my first CVE number that I got assigned for discovery. So here what happens is that if you were calling hash, or actually init update final and any calls of update, if one of those calls would be at least 4 gigabytes, then what happens is the implementation enters into an infinite loop. So to try to see how NIST in its programs can find a way to detect these types of issues, we introduced at that time the NIST large data test. The large data test is just seeing, like, for some specific large inputs, does your implementation compute hash correctly? And what I found really interesting is, so I'll give a presentation now about a vulnerability that I found in the SHA-3 implementation by the designers. But there's actually another SHA-3 implementation where a bug was discovered at the same time, just stumbled upon it when I was looking online, like who's talking about SHA-3, right, when this was disclosed. And that's a bug in GNU-PG SHA-3 implementation. So there's no CVE number, but Red Hat bug ID. So it seems that whenever you introduce a new test for something, if it gives a hit on one implementation, there's a good chance that at some point down the line it might trigger somewhere else as well. Without further ado, let's go to the SHA-3 bug. I'm really excited to see that so many people are here. Like, the audience 3 years ago was a lot smaller. I guess quite a few people, not specifically here for the cryptographers track, have thought like, yeah, let's go for some of the crypto talks. So this bug was not there since the beginning. It was actually introduced since the final round submission of the algorithm, so since 2011. And then not disclosed until end of last year. So we did a coordinated vulnerability disclosure to make sure that the everybody is patching this vulnerability. And what you have is, if you're calling init update update final, where the first update is a certain number of bytes x, and then the next update is going to be 4 gigabytes minus this value of x. So these are the parameters for the SHA-3 in XKCP, the extended catch-up code package, which Python and PSP has integrated. If you look at the one in the submission itself, then it's actually 512 megabytes minus x. So there was a refactoring of bits to bytes. That means the test vectors are slightly different. In that case, what happens is that there is a buffer overflow when you're calling this second value, this second update. And this buffer overflow, there's a quite cool demo for those who are interested, shows how you can do arbitrary code execution. So basically you have some type of digital signature you want to verify, for example, on some firmware you want to check. Before it gets to the point where it will say your check has failed, there is a buffer overflow that happens and an arbitrary code execution where the code is part of the message that you've provided. And then you can execute some payload, and this payload will allow you to do things like turn on the webcam, upload, download files. Like it's it can be really interesting to see the reaction when I show this demo to people. They're like, no, don't film me, right? So let me go into the details of this bug to show you exactly what is going on here. I also have to mention here that, like the previous one had an infinite loop, here there is actually also a specific input that gives an infinite loop. And it's when you do x bytes and then 4 gigabytes, not without this minus x, but like a full 4 gigabyte call to update. So it is important that you're doing one call to update first, because if you don't do this first call, then for any input of any size, the hash will be computed correctly. So it has to be this sequence of 2 different calls that you need to do to trigger the vulnerability. So here I have 3 lines of code. And I mean, it's, my intention is, yeah, go ahead.
What are like the limitations on x? Like, is x anything, or does x have to be a relatively small positive value? Or?
Yeah. So the x doesn't have to, so the question was, does x have to be large or small, or what are the restrictions on there? So x has to be a certain value that ensures that there is still a partial block inside the buffer. So like if I go back to this first slide here, you process the message into blocks of a certain size. If you do a call to update and there's still a part of a message that is not a complete block, that's going to be stored into a buffer. And that allows you to still use it when you later do a call to update if the block has completed to process everything. So it can be any value that is not a multiple of the block size, because if there's something left, then the bug will be triggered. Yeah, I mean, I'll continue taking some questions throughout the talk. Like if there's less time for Q&A, then we had that already during the talk, right? So here are the 3 lines of code that are problematic. And what I'd like to ask here is if anybody has an idea of what line is wrong or what the problem is. Like any guess or like So typically an answer I would get is that people will say, this unsigned int, that looks very suspicious, right? But actually the unsigned int is also there in the fixed version. So that is not the cause of the buffer overflow. And then, yeah, I got people saying, well, maybe it's then the second line or the third line, or like, I mean, you can just, there are not too many places where it can be, right? So let me show you how the bug is being fixed. Oh, animation is working. So here you can see more, so what I did here is like I took this partial block plus instance and I put this plus to the other side. Mathematically, this seems like exactly the same computation. This is how it's wrongly taught in schools, right? But it's a completely different computation because here, when you do partial block plus instance byte IO index, this addition might overflow for certain values. And that overflow doesn't happen when you move this to the other side. And now it also becomes more clear what the operation actually is. Because the operation is, we have this value of partial block. And if we have partial block larger than some value, we set partial block equal to that value. So this is actually a minimum operation that we're doing. We're trying to find the minimum of partial block and this rate in bytes minus byte IO index. But the minimum is implemented incorrectly in a way that might allow for an overflow. But if you want to look at the final fixed code, there are 2 more steps that are done to get there. It was a bit, like I said, the buffer overflow wasn't caused by this unsigned int, but actually the infinite loop is related to that. So you're not supposed to use the value of partial block here because you drop the higher bits. You're supposed to use data byteline minus I. And then instead of writing partial block and then writing it again, here you can see how the designers decided to fix the implementation in the final version of, the updated version of the XKCP extended catch code package. So I want to get a little bit into how the vulnerability works and what the details are, and then I have to show a bit about how the hash function works. So SHA-3 is a sponge function where this message that I showed being processed in blocks is actually XORed in. So here you see each of those blocks. And that allows you, if you look at how the vulnerability works, that allows you to XOR in not just the part on the top, but the part on the bottom as well. So not just the R part, but the C part. And actually further down, you can access internal memory parts as well. You can XOR some value. So here's the first attack you could do to construct a second preimage. Because basically, when you're XORing in all zeros, using these 2 calls, X and 4 gigabytes minus X, then you'll get to a state where it appears as if you process nothing. So similar to what you had in the case of Blake, that allows you to have one hash, and like a message and a given hash, construct a different message that has the same hash. You can also construct a preimage of any hash value if you work backwards, because SHA-3 has a cryptographic permutation, so you can evaluate both f and f minus 1, work back, see what the value is of the full state that you need at this location, and then work backwards, see what the message is supposed to be to hit any target value. And then here, this seems to be like what's more exciting. If you have the possibility to execute code, and like you have to discuss more like vulnerability-related things, like when this may or may not be feasible, then here I show a simple return to stack exploit. So I'm overriding the return address of the function that you've just that you're in to point not to where the function is supposed to return to, but to point to some place inside the payload. And then this will typically be like a little bit of shellcode that will, or a little bit of payload that will download some more payload and allow you to take over the computer and pivot deeper into the target. We introduced a new test last time. That was this init update. No, the last time was this large data test, LDT. Here's another test we're proposing, the init update final test, IUFT, to basically consider this case where you're doing a small input and then a large input and see if this is computed correctly. There's also some work in progress. I mean, a lot has happened since this vulnerability has been announced, and I just want to give like a small glimpse. So here is some code that is found as a result of a query that I wrote. It's a collaboration with GitHub Security Lab, using CodeQL to look for, is this specific pattern, like this incorrect way of computing a minimum, is this present in some other places of code as well? So GitHub allows you to scan over all of your GitHub repositories for free using CodeQL and see if there are some hits. And here is a hit that was found in OpenSSL and Boring SSL. You see like OpenSSL memcopy, right? Gives it away a bit where the code is coming from. Here it is not something that can be exploited. That's why I feel comfortable to show this slide. because a further analysis of the code shows that this done plus to do can actually not overflow in the specific case of this implementation. But it's still something that people who are doing static analysis tools feel that should be flagged, because you need to do quite a lot of analysis to see that it cannot overflow. And maybe you want to write it differently. Maybe you just want to write if to do larger than outlen minus done, to do equal to outlen minus done. You can see immediately you're doing this minimum calculation, right? So I want to move to my last slide and leave a little bit of time for Q&A as well. This is actually, I'm cheating here, the exact same last slide that I showed 3 years ago, as I think it still applies. So RSA wants apply what you learned today slide. So I do want to make a statement that I feel whenever you find a vulnerability, that it should not be the end, but the beginning of some process. Instead of just saying, let's patch and forget, we figured out this one, so many other vulnerabilities to deal with, could there be potentially systematic ways of avoiding this vulnerability? And I would like, if this is like a take-home message for you guys, to dive into your own experience, discuss with your colleagues which types of bugs that you have found. There are quite a few people who reached out to me already who have some really exciting stuff that I'm working on right now. So please reach out to us and let us know what types of vulnerabilities, bugs you find in cryptographic code, and it will be really interesting and exciting to follow up. So I'll conclude my talk here and leave like a few minutes for Q&A. Thank you very much for your attention. Yeah, 3 years ago, I had Adi here in the first row, and he was like, yeah, go ahead. You may want to move to the microphone, or yeah, then I don't have to repeat the question for the audience.
So it's a basic question. So it's just to know if, so far you know if most of the libraries that has this vulnerability have been patched, or how is the progress in the
This was a question I wasn't hoping to get, so what I can say is that, and as I mentioned, right, is that we coordinated with the designers of XKCP and the people who wrote the catch submission package and then the library afterwards, and with the upstream developers of Python and PHP. And also we assigned it a CVE number was assigned, and this gave it a score. So I can say that the vulnerability has been fixed upstream. Is that, I don't want to go, I mean, it's also really difficult to know where exactly this code is located, so we only have a visibility of open source code. Whenever this is in closed source code, then we don't actually know so much about where the code occurs and what, yeah.
It means that it has fixed in the source, so now the networks have to look for the part as well. So but in that area, you don't know.
I mean, RSA asks us to be neutral, right? Not say like this vendor is maybe dragging their feet a bit with regarding fixing it, but I think you've answered your own question. Like, yeah.
Question in that case
Yeah.
is, do you have a way to test? Isn't the GitHub some like a testing you can do to verify if the hashing function that you're using is proof against this vulnerability?
Yeah, so to find this specific vulnerability, you can look at like test vectors, because we give test vectors to see if the output like should be correct or not for a specific value. You can look at whether the code pattern is there. You could look at which version you're using. I mean, there are several ways to tackle this problem. And CodeQL was just another way of showing if you have the pattern somewhere, you can detect it. So I'm trying to work hard on this and find even more ways to see how can we find specific patterns to, or different ways to try to detect this vulnerability. Yeah, I don't want to take away any time from Leah because she has we have a great talk lined up for the rest of the session. So yeah, thanks again for your attention.
Okay, thank you very much. I would like to talk about cryptographic implementation, optimizations and trade-offs for HELOP. Never just read the slide aloud, which is a joint work with Anna Maria Kostake and Rachel Player. And so the broader context of this talk is fully homomorphic encryption. To quickly recall what fully homomorphic encryption is, it essentially allows us to compute unencrypted data. So the idea is, say we've got one person, call her Alice, that has some data but doesn't have the sufficient computational power to perform a computation on it. And we have some provider who could perform that computation for her, but Alice doesn't want that provider to see her data. Then fully homomorphic encryption allows her to encrypt her data, send it over, and then on the other server, the function can be evaluated on the encrypted data. That still encrypted result is getting sent back to Alice, who decrypts it and gets the plaintext evaluation of the function on her data that she wanted. And so in this broader context, what I would like to talk in particular about is one specific fully homomorphic scheme, that is BGV, and even a specific implementation of the scheme in HELOP, and one specific problem, which is noise analysis. And so the outline of the talk will be to first establish what is this noise in FHE, how can it be analyzed, and how does this lead to optimizations. So what is noise in FHE? Since I said I'm going to talk about one specific FHE scheme, I'm also directly going to illustrate what is noise in this particular scheme. And so this is the decryption function of BGV. So we've got a ciphertext that got somehow formed, a secret key that got somehow formed. And then the way that we're decrypting things in BGV is we're taking the scalar product of the ciphertext and the secret key, modulus the ring modulus, modulus the plaintext modulus. And then this gives us an expression like here, which is the message plus the plaintext modulus times some E prime. And I mean, then we directly see, okay, if we take this whole thing, modular the plaintext modulus t, then this vanishes. We get the message modulus the plaintext modulus, which is exactly what we want, so we're fine. There's only one problem. Before we get to the joy of taking the whole thing modular t, we have this ring modulus here, the ciphertext modulus, which is here because simply we're working in a ring modular qi. And so here we already can get an idea what noise in FHE means, because if this m plus te prime term gets bigger than qi, then we get a wraparound before we can take the thing modular t. But this wraparound may dissipate our dependence of this e prime term on t, so the modulus t step may fail to strip away this error. Then we get m plus something back, which is not the message that we want. And this is even more dangerous since the decryption will return to us something that looks like it could be a completely correct decryption result because it's in the right space. It could be fine, only it is not. So this is why this scalar product between the ciphertext and the secret key is called the critical quantity. And I hope I could make clear why it is a very critical quantity indeed. And this E prime or this T prime is often called the noise of the ciphertext. So now we could argue, well, why don't we just set our parameters in the beginning so that we know that m plus T prime never gets bigger than Qi, we don't get a wraparound, and we're always safe. Well, this would be a possibility if BGV was a normal scheme in the sense that messages get encrypted, sit patiently around and wait for being decrypted, and then get decrypted at some point. But BGV is an FHE scheme, the whole point of which is that the ciphertexts do not sit patiently around and wait, but get computed on, get changed. And so obviously, if you change the ciphertext, then we change the critical quantity along with it. So if we add two ciphertexts, the critical quantities get added. If we multiply two ciphertexts, the critical quantities get multiplied. So even if we set the parameters such that at the beginning everything is fine and we could correctly decrypt, this is no longer the case after we performed a couple of operations, and eventually it will get too big and decryption will fail. Which leads us to what I took the liberty of calling the FHE noise dilemma. In FHE, we need this noise so that the scheme is secure. But with too much noise, eventually we will not be able to decrypt correctly. So to exactly know whether we are still able to decrypt correctly, we would need to exactly know what the amount of noise is that we have at a given moment, but that again would break security. So the whole point of noise analysis is somehow try to work a way around this dilemma and of giving a good enough idea of what the current noise is without giving a so good idea that we would break the security of the system. So noise has been around in FHE schemes from the very first construction on, which means there are obviously techniques that have been developed to deal with this. One such technique or class of schemes are leveled schemes. And since this is quite important for the talk, I would quickly like to say what it means for BGV to be a leveled scheme. So essentially, we are choosing a chain of ciphertext moduli instead of just a single one. And this allows us to reduce noise by applying something that is called modular switching. And modular switching transforms a ciphertext CT1 that encrypts a message with respect to one ciphertext modulus into another ciphertext that encrypts the same message, but with respect to another ciphertext modulus. And since this is a little bit abstract, I made a very pink animation to illustrate this a little bit more. So normally we encrypt a fresh ciphertext at what we call the top level, at the biggest modulus. And then we could perform a couple of operations on it, and eventually the noise will grow dangerously big so that decryption may fail if we perform any more operations on it. Then we can essentially scale down the ciphertext by the ratio between the ciphertext modulus QL and QL minus 1, which gives us a new ciphertext at the next level that has small noise again. So now we can perform operations again because we again have low noise. And when the noise grows too big again, then we can modular switch again. And we can repeat this until we eventually reach the lowest modulus. Now, at this point, if the noise grows too big, we have to decrypt because there's no modulus underneath anymore. So we can't mod switch down. So here we can't do anything anymore. So I hope I already said a bit why we do need noise analysis in FHE, but maybe to give a few more points. Each modular switching consumes a level until we have no more. So we therefore want to delay modular switching as long as anyhow possible. But if you're delaying it, that means we're getting closer and closer and closer to the point where our decryption fails. So we need to have a very good idea of what happens to the noise. And we need so the tighter our estimates of the noise are, the more operations we can squeeze in before we eventually have the modular switch. And also, since the security level of the scheme is dependent on the ratio between the noise and the ciphertext modulus, if you have a good idea of the noise, then this may allow us to choose better parameters. So then the obvious question is, well, how can we analyze the noise? And so there are a couple of techniques that have been proposed. The first one is to bound the canonical embedding norm of the critical quantity. The canonical embedding norm has very nice mathematical properties that make it easy to bound, but also the bounds that we're getting are quite loose. So then the idea is to bound the infinity norm after each step in the circuit. The infinity norm gives normally tighter bounds, but also does not have so nice mathematical properties, so it's more difficult to get a bound on it. And also, if we bound it after each step, then we get this approximation error from our bounds in each single step. So if you have particularly deep circuits, the approximation errors are going to add up, and we are going to get looser and looser and looser bounds the further we proceed in our computations. So then it was proposed to bound the infinity norm of the complete circuit at the end to only get this approximation error once. And so this is essentially what we've been doing, and applied this technique to BGV. And also, we provided an implementation-specific noise analysis for one implementation of BGV in HELOP. And so then we compared our results with previous analysis of BGV noise and showed the need that doing an implementation-specific noise analysis actually is important. And then we used the results of our analysis to provide better parameter sets for BGV. Okay, so I said we did it like in 5. So now the question would be, okay, what does 5 actually do? And so the idea is to track the variance of the critical quantity, because we've got loads of randomnesses involved in BGV, so we can regard the critical, or we can model the critical quantity as a random variable, and then we track the variance of this random variable throughout the circuit. Then essentially proved that after most operations, this random variable is distributed like a normal variable. And then we can just bound the infinity norm by 10 times the standard deviations with a failure probability of 2 to the minus 75 plus the logarithm of the ring dimension. Okay, so then we merrily went off and calculated all the variances through the circuits. And then as a sanity check, compared that to experimental results. So we calculated the point estimator of the standard deviation of the critical quantity through looking at 8 different parameter sets over 1 to 5 multiplication and 10,000 trials in HGLOP. And so this is an example of the results that we got after modular switching. And so the first column here has the parameter sets that we looked at. So the first one is the ring dimension. The second one is the multiplicative depth that allows this parameter set. And then the second column is our theoretically obtained standard deviation in bits. And the third column is our experimentally obtained, so the point estimator of the standard deviation in bits. And so then 1 to 5 is the number of multiplications that have been performed. And so then we see in the column that is marked in red, this is the deviation that we observed between the experiments and the theory. And so here already we can see that mostly this deviation is below 1%, but for in one single case where it is 1.12%. And this is good news insofar, as I said, we ran it over 10,000 trials. So the to be expected standard error that we should be getting between experiments and the true value would be 1 over the square root of n, which in our case would be exactly 1%. So we can more or less declare our theoretical results experimentally confirmed. And a second interesting thing that we observed is we expected, well, if we are evaluating deeper circuits, that is, we're performing more computations, then the noise obviously grows and the standard deviation grows. But what we can see here, that this is actually not happening. And rather, the noise stays constant for a given parameter set, no matter how many multiplications we perform on it. And this is also very good news, because this means that we actually can use to bound the noise of 5 multiplications by using estimates for 1 multiplication, which means that for very complex circuits, it makes our life so much easier, because we don't need to concatenate very complicated bounds one after the other, but it rather gets quite simple. And so then we use these standard deviations to calculate the bounds, as I said on a previous slide, and compared these bounds with previous work. And so this is an example of what we got. So here in the first column, again, the parameter sets, then this column is the infinity norm that we experimentally obtained. B infinity is our theoretical bounds. And so 27, for example, is the bounds that we extracted from the HGLOP documentation, so the noise bounds that are currently being used in HGLOP. And so here we see that our theoretical bounds are at most 1.5 bits of the experimentally obtained bounds. And also that we improved upon the bounds in 27 by about 25 bits. And so then we did the same thing also for the noise. And so here again we see the parameter sets. These are the experimental obtained bounds on the noise. B infinity is our theoretical bounds. And 30 are bounds that have been obtained for Palisade, which is a different homomorphic encryption library. And so here we see like our theoretical bounds are at most 0.9 bits off. But what's far more interesting is to see that for the bounds that have been developed for Palisade, they actually underestimate the noise by 2 to 3 bits. And underestimating the noise is very dangerous, because then the bounds tell us that we can still perform more operations, although in reality we can't. And we may go on computing and not be able to decrypt correctly anymore at the end. So this is why I said before, it is very important to do an implementation-specific noise analysis, because while these bounds may work for Palisade, they clearly do not work for HGLib. So just saying, well, these two libraries, they're implementing the same scheme, so we can just take the bounds from one library and use them for another, is something that doesn't work. But we actually need to look at each library specifically. So now on slide 53, I'm finally at the title of the talk, Optimizations and Trade-offs. So how does all this lead to optimization and trade-offs? Well, so we really would like to keep this property that the noise is constant after modular switching because it's really convenient for everybody doing noise analysis. And so shuffling lots of arithmetic around from one side to the other shows us that we can make this work by either making the ciphertext moduli ratio smaller or by making a special modulus that we need for something called key switching also smaller. So then we fixed both in turn and looked what this gave us as optimizations for the other one. And so this is another table. So in HGLib, like the smallest ratio that we theoretically can get is 36 bits for the ciphertext moduli ratio, but we looked at over 20 parameter sets, and we never observed a ciphertext moduli ratio that was smaller than 54 bits. So then compared to the 54 bits with an error probability of 1%, we actually can get an optimization of 25 bits compared to what's currently used in HGLib. And if we fix the ciphertext moduli ratio to 36 or 54 bits in turn, then for an error probability of 1%, and say, for example, n equals 2048, the currently used value in HGLib is 45 bits for k, and we do get 19 with our updated noise and estimates. So here we have an optimization of 26 bits. So now, how does this lead to trade-offs? Well, I already said we can do either or. So when would we like to do either, or when would we like to do or? And so reducing the ciphertext moduli ratio essentially allows us, for the same bit size of the top modulus, like in the pink diagram that I had before, to just squeeze in more ciphertext moduli in between, and therefore have more levels, which would allow us to evaluate deeper circuits, essentially. If we're reducing k, that leads to smaller evaluation keys and a smaller key switching noise. And also, since the evaluation keys are smaller, this just speeds up the general key generation, which can be quite a bottleneck. So then obtaining more levels is of interest because it allows for the evaluation of deeper circuits. So essentially circuits that have more multiplications. Whereas reducing k can be of interest in client-aided protocols. So client-aided protocols essentially say, well, we don't want to deal with this whole business how to reduce the noise. So when the noise gets too big, we just send the ciphertext back to the client. They decrypt it for us, they re-encrypt it, then it has a small noise again, send it back, and then we continue to perform computations. So in this case, it is not so important to squeeze in more levels because we've got a nice workaround on how we can reduce our noise. But here, then we've got a lot of back and forth sending. So here, it then may be of interest to reduce the key generation time, to reduce the size of the key switching keys, because then we can save on bandwidth when we're sending stuff around. Yeah, so to summarize, the two things that I kind of wanted to convey are tight noise analysis in FHE is very important, and it's important to do implementation-specific noise analysis. And that's it. Thank you.
The question was about whether the magnitude of the noise remains the same after many multiplications or just the standard deviations, what was being shown on that table.
In the table, I showed the standard deviation, but since we bound the magnitude of the noise by 10 times the standard deviation, this also means that the magnitude of the noise stays constant.
So that seems counterintuitive that the amount of noise remains constant after many multiplications? Because it should multiply, right?
Yes, it does seem counterintuitive indeed. The secret lies in the modular switching, because that reduces the noise essentially and only leaves the rounding error. There have been a couple of noise-free schemes proposed. I have so far not seen one that has a security proof. And therefore, like, as long as there is no formal security proof of a scheme, it's hard to trust it. And also, I have not seen loads of cryptanalysis on them. So they have kind of been proposed, but then there's neither security proof nor cryptanalysis, which I don't say they don't work, but I would at least say they need further study. Okay.
All right, thank you, everyone. Thank you to Leah, and thank you to Nikki.